In this section, we're going to look at some of the different variables in the gas law and how they relate to one another. Specifically, those variables are pressure, volume, N, the number of moles, and temperature. So these are the variables we want to look at. Before we do that, I want to spend a minute to talk about the difference between a direct proportionality and an inverse proportionality. So in a direct proportionality, as one variable increases, another variable increases. I'm going to call them x and y for the sake of this example. As one goes up, the other goes up. This is a direct proportionality. In an inverse proportionality, if x goes up, y comes down. So they're the opposite. Mathematically, we can write this as xy equals a constant. I apologize. If we're writing a direct proportionality, we want to write it as x over y equals a constant. So as x increases, y, which is on the bottom, also increases, and if they're proportional, we end up with a constant value. In an inverse proportionality, it's xy equals a constant. So as x goes up, y has to come down in order to keep the constant constant. Another way you can write this is x1 over y1 equals x2 over y2. So the initial value of x is to the initial value of y, as the final value of x is to the final value of y. And here we could write it as x1 y1 equals x2 y2. Again, the initial value of x is to the initial value of y, as the final value of x is to the final value of y. Now, why I mention this is we're going to look at several variables in the gas law, again, pressure, volume, amount of gas or moles, and temperature, and decide whether they're directly proportional or inversely proportional. And then we're going to do a series of examples where we look at those things. So let's first look at the temperature and pressure relationship. So we're looking at the relationship between temperature and pressure. As this gas is heated by turning the hot plate on to medium and then finally on to high, you'll notice that the pressure increases. Well, why is this the case? This is the case because the molecules of gas inside of the container are moving faster. If those molecules are moving faster, they're hitting the sides of the container more often and with more force. Since the force with which and the amount of force they exert when hitting the walls of the container is the pressure is increasing because the gas molecules have more energy and exert more force on the walls of the container. So this increases the pressure. Notice that when we're comparing temperature and pressure, we're keeping the other two variables constant. Namely, we're keeping the amount of gas in the container, the moles, constant. We're also keeping the volume constant. This container doesn't change in size. So since the moles and the volume are constant, we can relate the temperature and the pressure. Temperature and pressure are directly proportional. As you heat this gas up, the pressure also increases. However, there's something important to note about this. That temperature has to be in Kelvin, the absolute temperature scale. Note that for all gas law equations, if they involve temperature, the temperature has to be in Kelvin. If you take an example here in Celsius, if we double the Celsius temperature from 50 to 100, we don't even come close to doubling the pressure. It goes from 77.5 to 88. It would have to go up to over 150, actually 155, if we doubled the pressure. But if we approximately double the Kelvin temperature from 173, if you doubled it exactly, it'd be 346. We'll look at 373. You approximately, again, double the pressure. It goes from 36, exactly double would be 72, but it's a little bit more, so it's 77.5. So the temperature has to be in the Kelvin scale whenever you're dealing with gas laws. So we've talked about temperature and pressure are directly proportional to each other. So therefore, we have these two variables related to each other, and we can come up with a Montan's law. which is P1 over T1, the initial pressure over the initial temperature, equals the final pressure over the final temperature. And in this case, we need to remember, as I said before, that the temperatures must be in Kelvin. So now I'd like to switch to the lecture notes and do an example. So in this example, it says, what pressure on a gas in a closed container, fixed volume, is 782 torr at 22 degrees Celsius? What is the pressure on the gas at 115 degrees Celsius? So essentially, we have a gas at 22 degrees Celsius and the pressure is 782 torr. We heat the gas up to 115 degrees Celsius and we want to know what the pressure is. Not surprisingly, we're going to use the equation at the top of this slide. P1 over T1 equals P2 over T2. But if you'll recall, we have to convert these temperatures to Kelvin. So add 273. When you do that for the first one, you get 295. Let me rewrite that. 295 Kelvin. Note that in some books they use 273.15. That just has more decimal places or more significant figures, and you could use that as well. So I'm just going to do it like that. In this case, we want to add 273 to this one as well to convert it to Kelvin. And when we do that, we find out that it's 388 Kelvin. Now that we've converted our temperatures to Kelvin, we can plug in. In these equations where we relate two variables, it doesn't actually matter what unit the pressure is in, because it will cancel out. It does matter what unit the temperature is in, because Celsius and Kelvin are not proportional directly to each other, so you do have to convert it. However, the pressure in torr, or the other unit of pressure you learned, atmospheres, are proportional to each other, so it doesn't matter which one you use. Anyway, the gas is initially at 295 Kelvin and 782 torr. So let's plug that in. First, I'm going to put the 782 torr in, and then I'm going to put below it the 295 Kelvin. So that's initial pressure and initial temperature. The final pressure is the thing we don't know. And the final temperature is we heat it to 388 Kelvin. Multiply the two numbers across from each other together, and then divide by the number that you multiply across from the variable. So essentially you cross multiply, and that'll give you 295K times P2, then divide by 295K. And when you do all that math, you find out to three significant figures that the final pressure here is 1030 torr. And again, I rounded it to three significant figures, with that last zero not being significant. So this is how we could find the final pressure. Note that in these questions, you'll be given three of the variables and asked for one of them. Now that we've talked about pressure and temperature, let's talk about temperature and volume, or volume and temperature. So the volume and the temperature are again related to each other. The temperature has to be in Kelvin. Well, what's going to happen? If you heat this gas up, the piston is going to expand. These gas molecules will have more energy, which will move them farther apart. If you remember earlier, we looked at a hot air balloon, which can float. When the gas molecules are warmer, there's more space in between them. Since space doesn't have any mass, you essentially have a lower density gas. This lower density gas can then float, just like a helium balloon floats in air because it's less dense. A hot air balloon can float as well. So as we heat up this gas, the volume increases. So as temperature increases, volume increases. That's a direct proportionality because both increase. Just like in the case of the pressure in the volume, or excuse me, the pressure and the temperature has to be in Kelvin. And this is true for all gas law stuff. So make sure that we're converting the temperatures to Kelvin. Here, someone has graphed the Kelvin temperature versus the volume and gotten a straight line because there is this direct proportionality. This leads us to Boyles Law, which is V1 over T1 equals V2 over T2. I would like to do an example of this, again, using the notes. It says, what is the temperature of a gas if 22.4 milliliters at 32 degrees C has a volume of 84.2 milliliters after being heated? So we take a gas, 22.4 milliliters of it at 32 degrees C. We heat it until the volume is 84.2 milliliters. And we want to know, well, what's the temperature once it gets to 84.2 milliliters? Just like in the previous one, we're going to use the equation right here, V1 over T1 equals V2 over T2. Don't forget to convert the temperature to Kelvin, so add 273. When we add the 273, we find that this is 305 Kelvin. Now we can plug in. 22.4 milliliters is to 305 Kelvin, the initial volume and temperature, as the final volume, 84.2 milliliters, is to some new temperature that we're trying to figure out. Multiply the two numbers together, cross multiply the number in the variable, so multiply 84.2 times 305, divide by 22.4, and you find that the final temperature here is 1050 K to 3 sig figs, or if you wanted to convert it to Celsius, it would be 877 degrees Celsius. You're not required to convert it to Celsius, but if you wanted to, that gives you an idea. So you'd have to heat this up quite a bit, from 32 to 877, to cause this large of a volume shift. Let's look at some other variables. So here we're going to look at volume and pressure. So when we're looking at the volume and the pressure, we have to keep some things constant. And what we're keeping constant here is the amount of gas and or the moles, and the temperature. So here we have a gas essentially in a syringe. It's kind of hard to see here, but we look at what happens to the pressure when we push in on the syringe. So as we push in on the syringe, and if you've ever done this, you know the pressure increases as the volume decreases. So as volume goes down, it's hard to tell that I'm pointing down, the pressure goes up. So as volume goes down, pressure goes up. That is an inverse proportionality. So these are inversely proportional. Well, if they're inversely proportional, then we get this type of relationship. P1V1 equals P2V2. And this is called Boyles Law. And we'll do an example in a minute. But Boyles Law is very important to breathing. So here you could see what's happening. So when we breathe, we don't have a little fan inside of us that blows air into and out of our lungs. Instead, we use pressure differences. So when we inhale, essentially our diaphragm contracts, which makes our lung volume bigger. When the volume decreases, when the volume increases, the pressure decreases. So the diaphragm contracts, the lungs become larger. When the lungs are larger, the pressure goes down. Air travels from high pressure to low pressure. So it travels from the atmosphere to slightly lower pressure than the atmosphere, and the air travels in. When we exhale, it's the exact opposite. The diaphragm relaxes and contracts, which contracts the lungs. I should say the diaphragm expands, which contracts the lungs. The lungs, therefore, have a smaller volume, therefore an increased pressure. So inside the lungs, we have a relatively high pressure, which blows air out. So when we inhale, the lungs get bigger, the pressure goes down, and air rushes in. When we exhale, the lungs get smaller, the pressure increases, and it's higher than atmospheric pressure, and air comes out. And we can explain this in terms of Boyles Law. And Boyles Law is P1V1 equals P2V2. Note what we're keeping constant. We're keeping the temperature constant, and we're keeping the amount of gas constant if it's an example like this. We don't change the amount of gas in the syringe. So let's do an example here. The question says, to what volume does a gas expand if 28 milliliters of the gas have the pressure decreased from 765 torr to 125 torr? So we have 25 milliliters of gas at 765 torr, and we decrease the pressure around it to 125 torr. And we want to know, well, what happens to the gas? it's certainly going to expand because the pressure around it has decreased. And we're going to use Boyles Law. P1 V1 equals P2 V2. So the initial pressure is the 765 torr. The initial amount of volume of gas that we have is the 28.0 milliliters. The final pressure is 125 torr. And the final volume is what we don't know. That's V2, that's the variable. So here we multiply these two numbers together, divide by this one, and when we round to three significant figures, we find that it's 171 milliliters. So when we decrease the pressure around the gas from 765 to 125, the volume increases from 28 to 171. This is an inverse proportionality. The pressure went down, the volume went up. It's also important to note we kept the amount of gas, the moles, constant, and we also kept the temperature constant when we did this. So next, we want to look at another gas law that relates the amount of the gas and its volume. So here we have some amount of gas, and here we have twice as much gas. Well, if we double the amount of gas here, we double the volume. This is very much like blowing up a balloon. If you want to make the balloon bigger, you blow more gas in. So the volume and the moles in chemistry and the ideal gas law, moles is what we use as the term for the amount. If volume and moles are going to be directly proportional. As moles of gas increase, the volume gets bigger. As you blow more air in a balloon, the balloon expands. So this is called Avogadro's law. V1 over N1 equals V2 over N2. And let's do an example with Avogadro's law. So here it says, what is the volume of a gas if a sample of 2 moles of gas with a volume of 87 milliliters is filled so it contains 8 moles of gas? So we want to use V1 over N1 equals V2 over N2. So the 2 moles of gas has a volume of 87 milliliters. Then we want to blow more gas in so that it has a total of 8 moles of gas, and we want to know what the volume is. So the initial V is your 87 milliliters. Your initial amount of moles is 2.00 moles. Your final volume is the variable, and the final amount of gas is the 8.00 moles. Cross multiply, then divide by this one, and what you find out is V2, the final volume, to 3 significant figures is 348 milliliters. So essentially, we made 4 times more moles, so we made 4 times more milliliters as well. This is Avogadro's law. So now we can kind of combine all of these terms. And when we combine all these terms, we come up with what is called the ideal gas law, which is all the variables in one equation, excuse me. So here we have PV equals nRT. Pressure times volume equals N, the number of moles, R, the ideal gas law constant, times the temperature. The temperature has to be in Kelvin. In all of the previous examples that we've looked at, we have seen that the units for pressure, volume, and moles don't matter. The units for moles is just moles, it is a unit, but the unit for pressure and volume didn't really matter. But in the ideal gas law, it does. And the reason it does, or one of the reasons it does, is because of this ideal gas law constant. The R, the ideal gas law constant, is 0.08206 liter atmospheres per mole K. This defines the unit of all the other terms. The volume has to be in liters. The pressure has to be in atmospheres. The amount, N, has to be in moles, which is just moles, and the temperature has to be in Kelvin. So this, when you're using the ideal gas law, you have to make sure that you convert the units appropriately such that they're going to work with with the ideal gas law constant. Another thing that I want to point out before we move on to going through a couple of examples is if we look at PV equals nRT. Let's pick two variables that are on opposite sides of the equation. I'm going to pick volume and temperature. If you notice that they're on opposite sides of the equation, it means they're directly proportional. V1 over T1 equals V2 over T2. This is called Boyles Law. If they're on the same side of the equation, and they're related to each other, they're inversely proportional. So pressure and volume is P1 V1 equals P2 V2, and this is called Boyles Law. So if we just look at the opposite ideal gas law, if they're on opposite sides of the equation, they're going to be directly proportional. If they're on the same side of the equation, they're going to be inversely proportional, like so. So this is very important to note, so you don't have to memorize any of those individual gas laws. And sometimes the variables aren't related, like temperature and moles aren't really related to each other. If you increase the moles, it shouldn't increase the temperature, for example, at least not for this reason. So this is basically that. If the variables are related to each other and they're on opposite sides of the equation, they're directly proportional. If they're on the same side of the equation, they're inversely proportional. Now that we've looked at that, let's do a few examples using the ideal gas law. Remember that the ideal gas law is PV equals nRT, where the pressure is in atmospheres, V is the volume in liters, N is moles, R is 0.08206 liter atmospheres per mole K, and T is the temperature. So let's look. It says, what is the volume of nitrogen if 2 moles have a pressure of 755 torr and a temperature of 25 degrees Celsius? So if we start with PV equals nRT, and we're trying to solve for V, so we divide by P, we find that volume equals nRT over the pressure. Now we need to plug in, but before we do that, we need to convert some units. Because R is equal to 0.08206 liter atmospheres per mole K, these are the units of the individual things. So the volume has to be in liters, the pressure in atmospheres, the amount in moles, and the temperature in Kelvin. Well, we're given the amount in moles, that's good. We are not given the temperature in Kelvin or the pressure in atmospheres. So we need to convert this to atmospheres times, if we just multiply this whole thing by 1 atmosphere, over 760 torr, so we divide it by 760, we find that this pressure, when we take 755 and we divide it by 760, is 0.933 atmospheres. And the temperature, we add 273 to that, and we find that it's 298 K. So now we've converted the units appropriately. So now we can plug in our 2.00 moles, our R, 0.08206, I'm not going to write the units every time, and the temperature in Kelvin, that's 298 K. That's a 2. Sorry about that. And then we divide by the pressure in atmospheres, which is 0.933 atmospheres. When we do that, we find that the volume in liters is 49.3 liters. So when we're using the ideal gas law, we do need to remember to change our units. The last one that we're going to go over in this section says how many moles of gas are in a 825 milliliter container at 1.05 atmospheres and 322 K. So again, PV equals nRT. But in this case, we're trying to find how many moles. We're trying to solve for N. So we want to divide both sides by RT. N equals PV over RT. The pressure has to be in atmospheres. We're good to go. 1.05 atmospheres times The volume has to be in liters, so we have to divide that by 1,000, which is 0.825 liters. Divide by R, 0.08206 liter atmospheres per mole K. Liter atmospheres per mole K times the temperature in Kelvin. It's already given in Kelvin, 322 K. N, rounded to 3 significant figures, is 0.0328 moles. In this case, we've used the ideal gas law to solve these two problems. So if you're relating two variables and holding two variables constant, you want to use the individual gas laws, such as Charles' law or Boyles' law. If you are looking for one of the variables when you have several of the others, you want to use the ideal gas law to solve that.